And so I'm flipping two coins. P and Q are the unknown biases of the two coins. There are four outcomes, and then the probabilities are given by these expressions. So P and Q are between 0 and 1. These four numbers are non-negative and then sum to 1. So this defines a model in the three-dimensional simplex. So N is 4, and this is the picture. So this is this quadratic surface known as the Segre surface to geometers. And so being for two binary random variables to be independent means to be on that surface. If I'm on one side of the surface, I have positive correlation. If I'm on the other side of the surface, I have negative correlation. Down here at the lower right is the same picture, but now we take the symmetric 2x2 matrices, then we get a green curve. So this is the submodel obtained where P and Q have the same value. So these are two identically distributed binary random variables. Now in general, here's a tensor example. So if I have three ternary random variables, then we're speaking about 3x3x3 tensors. So N would be 27, but if the random variables are identically distributed, there are only 10 distinct entries. So the color coding here in this Rubik's Cube is according to symmetry, right? So you have a symmetric 3x3x3 tensor, then there are only 10 distinct entries, which you can figure out by bars and stars. And the color coding shows the 10 distinct entries in the cube. So again, if you have a 3x3 matrix, it has 9 entries, but only 6 if it's symmetric. And for a 3x3x3 tensor, there are only 10 entries distinct if it's symmetric. So this is an independence model. So this is the models we're interested in, measuring the distance for. So here's an explicit example. So this is the actual formula for the surface for 2x2 matrices. So the underlying distance is what's called the L0 distance in this literature. So basically, I have the four outcomes, 0, 0, 0, 1, 1, 0, and 1, 1. And then there's an obvious distance, just counting the number of disagreements. So the values that this matrix takes is either 0, 1, or 2. So the distance between heads, heads, and heads, tails is 1. And the distance between heads, heads, and tails, tails would be 2. So down here, this theorem gives you the answer. So the answer is the Wasserstein distance from your given distribution mu to independence. So the distance to independence is some expression in terms of mu1 through mu4, involving square roots and absolute values. And on the right-hand side, you have a case distinction. So I'm chopping up the three-dimensional simplex into various regions. To be precise, 12 regions here. And on each of these 12 regions, I have an algebraic formula. Looks like there are 8 cases, but they're actually 12 because there's an absolute value sign. So here's the absolute value of the 2x2 determinant. And that's another case distinction whether that's positive or negative. Here's the same thing, a little simpler. This is for symmetric 2x2 matrices. This is also known, the model here is also known as the Hardy-Weinberg curve. So this is the red curve inside the probability triangle. So now the triangle is cut up into 5 regions. You can see this in the diagram down here. Up here you have the formula. Just looks like 3 cases, but they're actually 5 regions. And on each region, I have an algebraic function of the probabilities mu1, mu2, and mu3 of the empirical distribution. And then the value function is given here. Interestingly, in the last case, the optimal point will be constant. So if your empirical distribution is in this rhombus shape, then the closest point will always be the top point of this red curve. So the structure here is that I'm chopping up the simplex into semi-algebraic regions, and then on each semi-algebraic region, I have a formula that gives the optimal solution. So I like to discuss this general structure. So in general, we're solving an optimization problem, and the optimal value function, so that takes the data and computes the distance, and the solution function that computes the closest point are piecewise algebraic. So this suggests a division of this problem into two tasks. First, in blue, identify all the pieces. And then second, find the formula on each piece. Right? So here we saw this in the probability triangle into 5 regions. And then for our quadratic surface, for our independent surface, the tetrahedron was divided into 12 regions. And this is indicated here in these colors. Now, both the blue task and the magenta task have very high degree of complexity. So if you actually want to do this, there are two kinds of complexities that we have to address. The first task is a task of combinatorial complexity, right? So what are the regions? How many regions are there? And then the second task is one of algebraic complexity. We need to solve a system of equations, polynomial equations, and we'd like to know how many solutions are there to give us an upper bound on the critical points, number of critical points of our optimization
problem. Bernd, there's another question from Theodoros. So when do you choose the L0 metric or L1 metric?
Well, they're both used. So this is really up to the user. So there's an L0 metric. People play with different metrics. So in this case of binary random, of discrete random variables, the L0 metric is quite natural, right? Because it's kind of the Hamming distance on the cube. So you have a general product, a Hamming kind of a Hamming distance on a product of simplices, this is quite commonly used in machine learning. But we have some results for various metrics, but L0 and L1 are the most common. So this brings us to our picture. So the green ball, this is really representing a surface. This is really the cartoon. The green thing is the cartoon for our model, the big green thing. The little green dots are the cartoons for the data points, right? So you have the data point, that's the little green dot. And then to calculate the distance from the little green dot to the big green model, we put a small unit ball, which is a polytope, around the data point, and we inflate it until the unit ball touches the model for the first time. So try to think about one of these, small data points here, put a small polytope around it, our unit ball, the dual to the AlCoVE polytope, and then you inflate it until it touches the model, and then the inflation factor gives us the distance, right? So now you can see again our two tasks, right? There's a task with combinatorial complexity, and this really boils down to describing the combinatorics of the unit ball. So this is something that's very familiar and dear to the heart of the participants of this conference. And then there is a second task. Once I've identified how the polytope, the unit ball, touches the green model, then there's this sort of algebraic question: what is the degree of the critical variety? How many complex critical points do I expect when I want to solve this to actual optimality? Right? So this is the task of algebraic complexity. And I'm going to say a few words and just a few partial results on both situations. So the combinatorial...
So before you move on, Theodoros asked, what does it mean to capture the ball?
What does it mean to capture? Oh, okay.
Yeah, maybe.
So I have a polyhedral norm. And so this cube here is the cartoon for a ball, an inflated unit ball. Right? So how do you measure the distance from a point to some model, for example? So you take a small ball around the data point, and then you scale it up. You scale it up until it hits the model for the first time. So the place where it touches for the first time, that will be the closest point. And then the inflation factor relative to the unit ball will be the distance. Does that make sense? I'm not sure I understood the question correctly.
Yeah, that's okay.
Yeah, okay. Polytopes. Well, you all know about this, right? So let me just state one proposition. So if the underlying metric, the finite metric space, happens to be the graph metric on a graph, For example, for binary random independence of binary random variables, the graph would be the unit cube, and that graph happens to be a bipartite. If that is so, then the Lipschitz polytope has the following very nice description. The facets just correspond to the edges of this graph. This is an undirected bipartite graph. And the constraints are simply xi minus xj is at most 1 in absolute value, right? So these polytopes already made an appearance at this conference. They are really the symmetric edge polytopes that Laura Escobar mentioned in the second lecture yesterday. Here's an example. So the cube is particularly important because these are binary random variables. So the model, if I have k binary random variables, so the graph, the bipartite graph is the k cube, and then the vertices of the AlCoVE, the associated AlCoVE polytope, the associated polytrope, are the proper 3 colorings of the cube, of the graph, with one vertex having a fixed color. And then here are some numbers, and this grows, and I'll leave it to you to think about this some more. So we computed these with Polymake and other tools for some small independence models of interest. And I think pursuing these polytopes and looking at the polytopes that actually get used by machine learning people, I think could be an interesting direction for combinatorics and people who study F vectors and H vectors. So keyword here is symmetric edge polytopes, and these are special cases of AlCoVE polytopes. Now, I like algebraic geometry, so let me talk a little bit about the algebraic complexity. So suppose the model M is smooth, and it's an algebraic variety. And suppose you have a linear functional script L on the ambient space and an affine linear space of some dimension R. And let's say everything is in general position relative to each other. So I have a model, a linear space, and a linear functional. Then here's a theorem that says the polar degree, delta R of the model, is the algebraic degree of the red optimization problem. And the red optimization problem is to minimize the linear functional over the intersection of the model with the affine subspace. So there are 2 ways to think about this statement. If you know what a polar degree is, then this is a theorem. If you don't know what a polar degree is, then you can take that as a definition. Okay, so you can think about this either as a theorem or as a definition. Now, if you think about this as a theorem, there are formulas. In particular, there was a nice recent dissertation by Luca Sotomaco that gives a formula for all independence models. So for a geometer, an independence model is called a Segre-Veronese variety. And for example, the K cube, so as a variety, this is the K-fold product of the projective line, you get this kind of formula. So the delta, the R minus first polar graphs, is this expression. So this is a function of K, S is the summation index. Now I should say there's a lot of combinatorics behind here. So in Brown, there's some keywords, chow rings, Segre classes, and all that. And really what's behind here is the kind of co-normal geometry of which we saw a combinatorial shadow in Federico Arila's talk yesterday morning, right? So the polar degrees can be really defined as the cohomology class or multi-degree, to use Anna Wiegand's notation. It's the multi-degrees of the co-normal variety of the rank variety. So there's a lot of very nice co-normal geometry in the background, Lagrangian geometry, and it was very nice to see Federico's talk that sort of established the connection to combinatorics. Let's look at some numbers, right? So it gets exciting when algebraic geometry meets numerical mathematics. So here I have a table. This is simply the case of 2 discrete random variables. So for example, here I have 2 random variables with 4 states. So A, C, G, T. So my ACGT and Liam's ACGT at some particular point in our genome. and that's the independence model. So we're inside the 15-dimensional simplex. I have a 6-dimensional model, and these are the algebraic degrees. These are the polar degrees. So there's the unit ball, and it can touch, as in the cartoon, in faces of various dimensions. And for each touching dimension, I have to solve a system of polynomial equations if I really want to have a certified answer. And then these are the numbers. And so there are formulas in general that give this, and this is where we use intersection theory. We did lots of experiments. It's really quite an experimental paper, both on the combinatorial complexity. Here is the F vectors of some of these polytopes, and on the numerical algebraic geometry of actually solving these equations. So this notation, for example, here, this means it's a 3-dimensional cube. Everybody knows the F vector of the 3 cubes, 6, 12, 8. And then here are some other polytopes. And you can see here we see the distribution in probabilities of how often the polytope touches the green model at a face of various dimensions. There's often a prevalent dimension in which this touches, but we don't have any hard results. Nobody minds if a talk ends a little early, especially if it's the last talk of a workshop. So this is my conclusion slide. So I mentioned the Wasserstein distance to independence. It's a topic where statistics, optimization, and algebraic geometry interact in a nice way. And what I was trying to share in this lecture is there are very nice opportunities for algebraic combinatorics in studying polytopes, polyhedral norms, and relating them to both interesting algebraic geometric concepts and to topics that machine learners and PDE people care about. Thanks for your attention.
Great. Thank you very much, Bernd, for a wonderful talk. Yeah, and so there's at least one question that came up in the chat towards the end of the talk. So Rudy asked, what is the k-bit independence model?
Oh, so k-bit is so just k binary random variables. So n, the number of states. Let's go back. Oops. So this picture is the 2-bit independence model. So here k is 2 and n is 4, right? So I have a 2x2 matrix or 2x2 tensor. And so this is simply the independence model for k equals 2 binary random variables. And then by k-bit, I mean just k binary random variables. So for a geometer, this is the Segre product of k copies of the projective line embedded in the projective space or a simplex of dimension 2 to the k minus
1. Got it. Thank you.
Great. So Serkin and I had similar questions, I guess. So Serkin asks, how about Wasserstein distance to almost independence models? So for example, decomposable models, reducible models, or toric fiber products.
Absolutely. So we focused on this case, of independence models because those are the most simple and most straightforward models to look at. But I completely agree. This would be very interesting to look at for other kinds of models. In fact, I think this would also be interesting even look at for finite point clouds. Right? So you have a finite point cloud, and maybe you're interested in the Wasserstein-Voronoi decomposition, right? So which point is closest to a given point? So you could study Voronoi diagrams. So I think there are lots of interesting opportunities for algebraic and polyhedral combinatorics.
Great, thank you. And then Alex Heaton asks, on some slides, there was an affine linear space L. Where did it come from? Is it the face of the unit ball polytope that touches the model?
Yes, exactly. That's basically exactly. So it's actually the linear span of a face. So in the L, so here in the L, when we model this in terms of polar degrees, so L, so if I have an I-dimensional face, think about the data point being the origin inside the ball. So this I-dimensional face will span a linear space of dimension I plus 1. And that's really the one I'm intersecting with the model. Right? So the L here is the linear span of an I-dimensional face when I think about my green data point as the origin. That will pierce the model, and then I need to solve this red optimization problem to calculate the Wasserstein distance, assuming that that was the correct face.
Great. And then just one more question from Theodoros before we go to the poster session. So Theodoros asks, why assume M compact? Is it for existence of solutions?
Yeah, exactly. It's just a technical hypothesis. So if M is compact and I'm inside the simplex, then I'm assured, that then there will be an optimal solution. There will be a solution to my optimization problem, and then I can speak at this being critical with respect to some stratum, just for the simplicity for the optimization problem to make sense.
Great. Okay. So thank you very much, Bernd. Thanks again. So.